On the board here are our 6 basic functions and their graphs. This first one is our linear function, which is represented by f of x equals x. Our second graph is for a quadratic function where f of x equals x squared, and this creates a parabola on our graph. Our third function is f of x equals x to the third. This is our cubic function. Our fourth is our rational function where f of x equals 1 over x and x is in the denominator. Our fifth is our absolute value function where f of x equals the absolute value of x. And our final one is our radical function where f of x equals the square root of x. Now it's very important for you to become familiar with all 6 of these graphs. That'll help you with your work with transformations in this section. Now a transformation of a graph is when we include different numbers in the function, and those numbers will affect the shape or location of your graph. And so we can move these graphs around either on the coordinate plane or we can reflect them about one of the axes. We can even scale them in size up or down by adding in different numbers into the functions. So let's try a few of these transformations. This first problem involves vertical translations. So we're asked to find the equation for the blue graph. So we're given a red line here, which is represented by the equation y equals x. And we need to figure out what equation represents this blue line. So according to the rule for vertical translations, if we take our original function and we add a constant to it, we add k units to it, then that means that we just move our original function up k units. If we were to subtract that constant from our original function, we'd move our graph down k units. So keeping that in mind, let's look at these two lines. Now they're parallel because their slopes are the same. Let's choose a point on the red line here. We'll just start right at 0, 0. And if we count how many units it takes to get from the red line up to the blue line, we get 1, 2, 3. So essentially we have moved this red line up 3 units. And according to our rule for vertical translations, we can rewrite the original equation and make it represent our blue line. So we have y equals x as our original equation, and the rule for vertical translation said that we add the number of units that this graph has been moved up, which is 3. So y equals x plus 3 is the equation that represents this blue line. So now let's move on to our next problem, and we're going to talk about horizontal translations. In this problem, we're given a graph and we're asked to identify it as a translation of a basic function and then write the formula for that graph. So at first glance, we see that this red line, this graph, looks very similar to the basic graph for a radical function, which is y is equal to the square root of x. And this graph, if I were to graph it quickly here, let's see, would look similar to this. And so as you can see, the red line that we were given looks very similar to the graph for our radical function, but it's just shifted, and it's shifted horizontally. So it looks like it's moved to the left a number of units. Now, according to our rule for horizontal translations, we can add a constant value to our variable within our original function, and if we add that k, we can move our graph that number, k units, to the left. Now if we were to subtract this number from our variable within our original function, then our graph would move that number to the right. So if we take our original function of y equals the square root of x, and then we look at where the graph of our red line lies. And so we see that our original point of 0, 0 for our original function, we've moved that 2 units to the left. Now according to our rule for horizontal translations, 2 units to the left, we can add the number 2 then to our variable x in our function. And we can rewrite then this as an equation to represent our red line. So we have y is equal to, under our radical sign, we have x plus 2. And then this is the formula that represents the graph of this red line here. And it's a horizontal translation of our radical function. So let's move on, and we're going to try some transformations where we scale the size of our graphs. For a final problem, we're asked to graph these functions on the same coordinate plane. And so the functions here, we have y equals 3 times x squared, and then we have y equals 1/3 of x squared, and the final one is y equals -3x squared. Now, these have a coefficient to this first term of our function, and we're going to follow a rule for scale factors and reflections when we deal with functions. And so the graph that we have here is for our basic graph, which is y is equal to x squared. Now, we have added in some numbers here, and that's going to change what our graph looks like. So let's start with the first one, y equals 3x squared. Now, if we look at our rule for scale factors, and this is for a function where y equals a times f of x, then we know that if the absolute value of a is greater than 1, then our graph is going to be scaled and it's going to be stretched vertically by a factor of that absolute value a. So for y equals 3x squared, 3 is greater than 1, so we know that the graph of this function is going to be stretched vertically. So let's see what it looks like. If we were to start with our y equals x squared, and then let's plug in some values here. Stretching vertically means that it's going to be a little narrower than our original basic graph. And so it's still going to start down at 0, 0, but for our next point, let's do 1, and plugging that in, 1 squared times 3 is 3, so we have a point of 1, 3. That goes the same for -1 for our x value, becomes 3 as well. And then if you were to continue and plot points, you'd get a graph that looks somewhat like this. So as you can see, it's going to be stretched vertically compared to our original basic graph of y equals x squared. So the red graph here represents y equals 3x squared. So our second function here, y equals 1/3 times x squared, according to our rule for scale factors, our graph is going to be compressed vertically if our factor or our a value is between 0 and 1. And so let's see what this graph looks like. If we were to plot some points for y equals 1/3 x squared, we'd get a graph that looks let's see, something like this. This is 1/2 of it, and then here's the other half. So as you can see, it's kind of flattened out a little bit. It's compressed vertically because 1/3 is our value for a, and that falls in between our 0 and 1 domain there. So finally, let's see what it looks like when we graph y equals -3 times x squared. Now, according to our rule, a reflection about the x-axis occurs when our a value is less than 0, and that's what we have here. -3 is less than 0. And so we're going to reflect our basic graph and then scaled by 3, but then it has a negative sign here. So essentially, we're reflecting this first graph, the red graph here, about the x-axis. And so if we do that, again, it's still going to start at 0, 0, and this is our x-axis, so we reflect it, and we're going to flip it upside down. And that will give us a graph that looks something like this. So there you go. So this is a graph that represents -3x squared. And that's a few examples on how you apply your rule for scale factors and reflection.